Hi, my name is Colin Ginge, and I'm going to kick off this webinar today. I see that most of the people are in their place. As we proceed, you can send us questions anytime, and we're going to focus on answering them later on in the presentation. I have kind of a bit of a formal session for about half an hour, and then I'm going to run a software program that we have that we offer for free called Pressure Event Calculator, so it does both the hold time and the pressure event calculation at the same time. And I think most of you have been sent a copy. Some of you have asked about an imperial and a metric version. We do have a new version that I'll have up on the screen. None of you have that version. It actually works the same way, but we've worked it out in such a way that it's a lot easier to understand. And by all means, fire questions at us at any time. We've got two people standing by that will be answering them in addition to myself. I'm assuming everyone's in place. So let's just start. I would like to run a poll, a couple of polls at the beginning of this so I can orient the presentation more towards where the listeners are at, and it might seem a little bit tedious, but it will really help to direct the presentation. The first slide I'll address, which essentially talks about the discharge test, which essentially before 1988 all systems are discharge tested, and it turned out it was costly, time-consuming, and disruptive, and shortly after that I proposed, or actually before that, in 1984, I proposed using door fans and an algorithm to test enclosures, because mostly they failed because they were too leaky. And of course, since then we've had NFPA 2001 and a lot of things. The latest thing that's occurred, of course, is the peak pressure evaluation, which is now mandatory, and we've been encouraging people to convert to our new software, which says peak pressure and hold time analysis, and tried to make that transition as comfortable for you as possible. I'm going to try to launch one of the polls. Oh, it looks like it's actually working. Okay, so the first question on the poll, see if I can pull it out here without destroying anything. The first question on the poll was about Enclosure Integrity training certification. That will give us an idea as to what level the listeners are at. So we're at the 68% level. I was reminded that people with iPads can't be involved in our polls. For some reason it doesn't work. So we'll just give you a moment to complete that poll. And at the same time, if you're done with the poll, you can dream up some questions you want to send off to us. We can usually respond to them right away. Now, I'm assuming I can close here in order to end that particular poll. So it looks like over 50% of the attendees haven't gone through our Enclosure Integrity training. Results of our first poll. So let's take a look at the first slide that we have here, which is on what we call a door fan test. So the door fan test has essentially replaced the discharge test almost universally, starting, as I said, in 1986, and I think that we have a pretty high level of door fan testing as opposed to discharge testing going on. There's the occasional time when a discharge test might be performed, but by and large the door fan test does that. It also, even if you are going to do a discharge test, it allows you to determine whether or not it will pass the discharge test. The new reason for doing it would be the door fan test can also evaluate the enclosure for peak pressure that would occur during a discharge. So even if you are discharging, and I know in a number of instances when a discharge test has been performed for full-time evaluation, they've unwittingly overpressurized the enclosure and caused damage. So if you do nothing else, you should be using the door fan test to check for that. Let me turn it back on. Okay, I'm sorry. I show my screen. Sorry about that. I'm just informed that I wasn't showing my screen. There we go. See, it's back now. So there's a little schematic down here that shows the door fan test, which is simply a fan which blows air into the room at a fixed pressure and determines how leaky the enclosure is. The test is somewhat involved, but the steps are relatively easy to follow. But that's essentially how it works. So it's a panel system that fits in the doorway, a blower which pressurizes the room, and a gauge which measures how leaky the enclosure is. So the next thing I want to talk about are some agent, I call them agent loss mechanisms. How does agent get lost from an enclosure? This is part of our level 1 enclosure integrity training. So the main driving force is gravity, which pulls the agent out. These agents are heavier than air, and gravity pulls them out of the enclosure, quite simply. And just like water in a cup, the more holes you have, the faster the agent is going to run out, which is what those two slides show. There's a lot of these things we're going to just jump over because we don't, it's not really a full training course. We're going to try and get to the important parts. There are large pressures that can occur during the discharge. People assume that because of these pressures, a lot of agent will be lost, but because they're so brief, that's actually a relatively small amount of agent loss. It's all taken care of in the design concentration, and by and large, the concentrations that we measure are far greater than the concentrations the equations deliver, because the assumption for the agent loss during discharge is a lot greater than it actually is. So if we discharge according to the equations 10%, we'll often get 10.5 or 11%. Now, during the discharge, there's convection that occurs, so things aren't all stable in the enclosure. That can be produced by hot equipment, which fortunately tends to suck the agent up into the equipment and protects it a little bit better than it otherwise might. If there's something hot in the room, for example, a hot wall heated by the sun, or a hot boiler or whatever, that will cause a convection current that will cause the agent to mix. In the case of an inert agent discharge, it will cause a convection current that will almost go up to the ceiling. For the halocarbons, they are heavier, and it only causes a convection current that goes up a foot or two. There's also forced air circulation, which is a very important concern because there's often an assumption that a sending interface will occur, which is agent goes in, agent leaks out, air comes in the top of the enclosure, so we have a layer of air and then agent below that. But in actual fact, what often happens is as the air leaks in, it gets continually mixed with the agent there. So instead of an interface forming, which is, say, equivalent to, say, water in a bucket where you've got air above and water below, we actually have a mixture, which might be more like steam in air, for example, so that the concentration changes everywhere in the room at the same time. Now, this is important to know because it occurs and people don't know it occurs. And often you want it to occur in situations where you want to protect the top 10 or 15% of the room. You pretty much have to have some kind of continual mixing or forced air circulation to do that. And usually the equipment that's in the room that has cooling fans in it, little cooling fans in the computer racks, are usually enough to cause continual mixing. And there's a test that we talk about in our training course that shows you how to determine whether continual mixing is in fact there. I'm thinking we might just try another poll here. Hopefully I don't mess it up this time. No, that's wasn't what I wanted. Let's see, so we'll try number 2. So this question is on what type of enclosure integrity software do you use? We have a new software package called FanTestic Integrity that a lot of you would have. There may be some other software you have. You perhaps aren't using software at all. That would be important to know. If people are entirely familiar with the software choices out there, we won't focus on it very much. But seeing so far that about a third of the audience use our old software, CA 2001, and we do have a replacement, a free replacement for CA 2001 for people that have purchased it in the last 2012, 2013. So certainly if you're in that category, there's no reason why you wouldn't want to take advantage of that, and we have that offer available till the end of December. So if you have bought our old CA 2001 in the last, in 2012, certainly let us know. So we'll just let that run for another minute or so. And I think I recognize now that when the poll is going that I can't show you another screen, so live and learn. Okay, I think we're getting to the point where most of the people who are going to answer have already answered, so I'll close that and share my screen again and carry on with more exciting stuff. Sorry, I'm just kind of jumping around here a little bit. So another thing that we have to determine when we're trying to figure out hold time or peak pressure is what's happening with the HVAC system, whether there are any leaky dampers that could be sucking agent out of the room, what's happening with wind. I recall once there was a discharge test done on the telescope in Hawaii, and they discovered that all of the agent on the windward side of the building was lost in seconds, so their wind was the driving force. I've made an effort to actually put a wind loss analysis into the software, and I've got it all completed, but nobody seems to think it's as important as I do, mostly because the enclosures that we deal with aren't affected by wind. But if you do have a situation where wind is or could be a factor, then we do have a solution to that. There was one in our old software, but not in our new one. So I won't bother going through the summary, but I will jump to standards. So I think we have a question on standards. Let me just see. What standards do you use? Okay. Let's launch that one and find out what standards people are using. So there's NFPA 2001, the 2012 edition, which is actually the same as the 2008 edition, but there were so many mistakes, hundreds of errors in the 2008 version that you can't actually use it. A lot of people will still be using an earlier version. There might be people from Europe online that are using ISO or the European norm, the EN standard, or another one, which I haven't heard about. It should be unusual. So we'll just wait for a minute, and if you've already completed the poll and you have some questions, that would be a good moment for you to fire it off to us. I think I'm showing my screen again correctly. So just for interest's sake, we've got 2/3 of all the attendees are using the 2012 edition. And the key thing you will notice in the 2012 edition is that it requests that you do a peak pressure analysis. And we're going to be getting into that later. Okay, so let's talk a little bit about standards. So we're only got 3% of the people are using a European standard, so we will touch on that. The European standard has is in the process of changing, and it has a requirement to do peak pressure analysis in it, but it's a little bit behind the NFPA standard in some other areas of the hold time analysis. I put in a proposal to the committee to change that, to make it a little bit less conservative, and those changes will be coming out in the next edition, which probably within the next year or so. So they will be changing to be a little bit less conservative than they are now. The NFPA analysis assumes what's called a sharp interface, and we've determined that even though there is no such thing as a sharp interface, there is kind of a zone that we transition from air to agent. The sharp interface analysis of NFPA is actually pretty close for most of the halocarbons, because what happens when they discharge is they cool at discharge. There's a fair bit of cooling, and during the hold time period, the agent is continually warming up, and the expansion of the agent during that period causes it to supply the lower leaks and causes a lot less leakage of air into the enclosure than we would anticipate, and just so happens that it matches the sharp descending interface very, very closely. In fact, for Novak, it's almost perfect. That's not the case with inerts. Inerts tend to run out a little bit faster than NFPA predicts, but it's pretty close. The ISO uses what we call a wide interface, which says it starts at 0, and as the interface drops, it keeps expanding. We've discovered that's not actually the case. The interface expands to what we call a characteristic thickness and doesn't really expand beyond that. And for halocarbons, it's about 0.5 meters or 1.5 feet, and stays at 1.5 feet as the interface descends all the way to the bottom of the enclosure. For inerts, it's about 1 meter thick. The only thing that we have to remember is that for inert agents, the NFPA is a little bit optimistic, and the ISO standard is a little bit too conservative. So what I thought was kind of cool is that the correct result is right in between the two standards. So a little bit about peak pressure. Perhaps before we do that, we'll take a look at another poll. We'll take a look at what agents people install. I'm assuming that most of the attendees will be installing both inerts and halocarbons, and in the surveys you can click all the ones that apply, and it's coming in that we've got pretty much even inerts and halocarbons, a little bit more on the halocarbon side. And we've also got a few people installing aerosols. So those of you that install aerosols will be happy to know that we will soon have aerosols in our Enclosure Integrity software. So there is a requirement in the aerosol standard that you do a hold time analysis, and we will have a hold time analysis for you very shortly in the next version. So the way our software works is every time you go online, it will download the latest version, and some of them are bug fixes, and other pieces are new developments. So something like aerosols will just magically show up one day as one of the agents that you can pick. So just for the sake of interest, we've got 7% doing aerosols. Surprisingly, 6% of the attendees don't install any agent at all. It could be that there are some equipment manufacturers who sell equipment, such as Fike. I know that Brad Stillwell is hopefully on the line. I know he registered. So he would be an equipment manufacturer, and I don't think they actually install systems directly, so I'm assuming that's where that would come from. Okay, so we got about 80% of you voted. Thank you very much. So we're just going to close that down. Go back to showing my screen again. And let's talk a little bit about pressure theory. So I'm hoping that I forgot what I was going to say. Sorry. I have many hopes. So we had a question there from Chris Reimer saying, will there be software for Vortex hybrid water mist? I think that's hybrid water mist. I would have to have, I guess the answer is no, we don't have any plan for it yet. I don't know that water mist has a requirement for enclosure integrity for hold time. If that's different, I'd sure like to hear about it. There's no reason why we can't do something like aerosols. The thing is, with some of the standards, they ask you to do things, but they don't tell you how, and that's the way the aerosol standard is aligned. So we're doing something that is very, very similar to what we're doing with 2001. The same thing is true with CO2. We have CO2 in our software, but if you look at NFPA 12, which governs CO2, it's not actually in there. It doesn't require an enclosure integrity test, but I know for a fact that is tens of thousands of CO2 tests have been done with our software. So hopefully that answers your question. So now we're going to go and take a look at a little bit about peak pressure theory. I started talking to the agent manufacturers 2 decades ago about peak pressure because my first just purely mathematical analysis told me that we would have excessive peak pressure, and sure enough we do. Most of the reasons why we have a problem with peak pressure is that no one's even thinking about it. I've seen several installations where they were making the enclosure as tight as possible. Nobody ever thought about peak pressure. So it's not a huge problem, but I would say there are probably more peak pressure negative events than there are fire events that are being put out. So it's almost like peak pressure can cause more damage than the fire suppression system can prevent in a lot of cases. So peak pressure depends on several factors. Main factor is how leaky is the enclosure compared to its volume. We call that the leak to volume ratio. So once you establish a leak to volume ratio for a particular enclosure, it's going to be more or less the same no matter how big or small the enclosure is. And each agent has a particular leak to volume ratio that's ideal for that agent. The VDS equations, for example, look at it in terms of mass flow rate, but it actually means the same thing at the end of the day. One of the surprises when we did the peak pressure research, which happened over I think 3 or 4 years, is that we discovered that humidity was a very big factor for halocarbons and not a factor at all for inert. So that's something later we'll talk about having to take into account. So this is a typical inert, a very short, sharp positive spike after about 5 seconds from the start of the discharge, and then it tapers off. If we take a look at halocarbon, for example, because there's cooling involved, a short positive spike because the agent coming into the room, as soon as the cooling starts to have an impact, the air contracts so rapidly in the room that we have a negative spike. And the size of the negative spike has to do with humidity. As the humidity goes down, the negative spike increases, becomes more and more negative. And the way I look at this is that you get more evaporation when the humidity is low. Like in the desert, for example, you get very fast evaporation. Once the humidity is at its maximum, the amount of evaporation or the amount of vaporization we get reduces. And for a lot of the agents, if we get close to 100% humidity, there's almost no negative spike at all, and it all becomes positive spike. So here we have, I think this is FM200, and we're showing the negative and positive spikes where we're only changing the agent leakage. So in this case, we go from 13 to 50 square inches in the same enclosure, and you can see as we go to the tightest enclosure, we have the biggest negative and the bigger positive spike. What we did when we did our analysis of peak pressure is we held the humidity in the enclosure constant for every discharge, so we weren't looking at a difference in humidity to get the characteristic curve of the enclosure leakage. So the leak to volume ratio is the most important. It's fairly easy to control, and if we find that we have an excessive pressure, which we will be able to determine with our free vent analyzer, which we'll look at it later, we may need to install a vent. I know it's been standard procedure in the U.S. to often install vents for all inert systems, and often that's required, but interestingly, you'll find out sometimes it's not required. And to never install vents for halocarbons, and often it is required for halocarbons, and it's not installed. So I would say that halocarbons require vents maybe 25% of the time, and some jurisdictions are not being installed at all. And I think that is a problem. So here we have a funky little graph that shows the effect of relative humidity on peak pressure. This line here, the red line that's dipping down, is the effect on negative pressure. As the humidity rises, the amount of, or the size of the negative spike gets smaller and smaller. That's all that shows. This is all incidentally in a paper, which I believe we sent out to you all in advance. It's about 10-15 pages or so that talks about all this stuff. So an important problem, an important situation that we've run across the last 20 years or so of testing enclosures is often we look at an enclosure and we go, oh my gosh, if they'd only done this, it would be really easy to pass. Well, now we've got two things that we have to worry about, passing not only hold time, but also peak pressure. So it's even more important in the design phase for whoever's designing the enclosure to be thinking about all of the parameters that are going to affect results. So we have to think about enclosure strength, how much leakage area we want, where our minimum protected height is going to be, how high the enclosures are, and so on. And in a paper I wrote on enclosure optimization, I talk about how you can control all these variables in the design phase. For example, if you were to take a room that was 14 foot high, put a 10-foot suspended ceiling in it, and then put the equipment at 9 feet, we would need a vent. If we got rid of the suspended ceiling and discharge agent in the room, we probably wouldn't need a vent. We'd have a hold time that would be 4 or 5 times longer, and we'd have better protection because we've got more agent there. In some cases, adding a little bit more agent is going to solve a whole lot of problems. And I know for sure that the biggest single problem that people have out there is getting small enclosures tight enough that they will pass the hold time requirement. And I've seen people spend $250 on a 250 square foot enclosure an entire week trying to get this enclosure tight enough. Now we discover not only did we have to spend a lot of money on unnecessary air sealing, but we also had to put in a vent on top of that, which may not have been in the original budget. All this can be figured out in the design phase, and most of the mistakes with enclosures are repeated over and over thousands of times, and there's not a lot of knowledge that's required in order to figure this out in advance, but it all can be figured out in advance pretty much so that the enclosure can be optimized for hold time and peak pressure, and in the long run probably give you better performance and spend a whole lot less money. So this is a section out of the new NFPA 2000 1, edition 2012. These are sections that we pulled out that talk about pressure relief venting. And I put the numbers in there. They're all in our training course, and they're also in the article. So it says pressure relief vent area must be adequate to keep peak pressures below a specified pressure limit. So now we have to specify a pressure limit, which often is not happening. Often it's left up to the tester to kind of make one up on the day that it's tested, and it should actually be in the specifications. Let's see. So specifying the pressure limit is kind of the same thing as the reciprocal of understanding the enclosure strength. So we can't specify a limit unless we know then how strong a particular enclosure is, and we'll get to that later. Here we are already. This is the only published document that I know of, and it was a paper, I believe, that Mark Robin did it about 10-15 years ago, and it's the only published information I've ever been able to find on the amount of pressure that different walls can withstand. Generally, what I say is a 2x4 stud wall, sheetrock on one side, will withstand 5 pounds per square foot. If it's double-sided, usually you can go to 10. If it's 2x6, you can go to 10, maybe 15. So 5 pounds per square foot is 250 pascals, 10 pounds per square foot is 500 pascals, and 15 pounds per square foot is 750 pascals. So often what's happening is there's an underestimation as to how strong the walls are, but there's also, as you will see later, an underestimation as to how much pressure is actually going to be created at discharge. Just going to take a look at our questions here to see anything interesting coming in. If you didn't get the paper, by all means, we can send it to you. So for David and Sam, who've asked for it, we have that question logged in here, so we can just shoot you a copy of that paper, no problem. So there are venting guides that we put out, FSA has put out, FIA has put out, and so on. The first three are kind of like one and the same. The halocarbon venting formulas that we're all using are the same formulas essentially. In a lot of cases, the agent manufacturers have their own venting formulas, and I can say quite honestly, from my own experience, if there's a difference between the two, the ones that we call the FSSA formulas are the only ones that I believe have been extensively tested. And by extensively tested, I mean tested over a wide range of leakage areas where humidity has been controlled, the leakage area has been properly measured, so we can relate leakage area to enclosure strength. Before they've measured peak pressures, but they've basically done the same discharge in the same enclosure without really understanding exactly what the leakage of that enclosure was. And it's really important that the measurement method that we use to measure the leakage in the enclosure is in the study is the same method that we're going to be using when we evaluate the enclosure. And I can say, because I did both on the FSSA study, or actually the results were published under FSSA, I can say that our test method for the study is exactly the same as the test method that is now in the NFPA standard, because I did them both, so they actually match up. So I can say without fear of too much contradiction that the formulas that we have listed in our software are correct. I think I have, here we go. The yellow line on the screen here represents the venting formulas. This is just for inerts, because there weren't any, pretty much aren't any venting formulas for most other halocarbons out there, or they're very, very few. That the yellow line is the venting formulas that we got measured in an enclosure under test conditions, under control conditions. The dashed lines are the various formulas that are provided by manufacturers, and you'll notice that just like the clock that is broken, they're right at each one of these crossover points, but at the area of interest, which is, let's say, around 500 pascals, even the most conservative of the manufacturer's equations are predicting almost half of what we got, and in some cases they're predicting a quarter of what we got. So there is a 100 to 400% error in a lot of the peak pressure formulas that the manufacturers are providing, not because they don't know how to measure pressure, but the relationship between how we measure the leakage during the test, during the research, and how we measure the leakage in the enclosure when the enclosure integrity tester goes out there were different. Now, the other thing that we have determined is that it's not necessarily the solution to the problem to simply put in a vent. And we found a lot of problems with that. One problem was for a very big inert agent manufacturer, who not manufacturer but installer on the West Coast. They had 3 PRV or pressure relief vent failures. And in one case, the manufacturer said it would open at a certain pressure, and it opened at 100 times that pressure. In another case, they were expecting a positive pressure, and what do you know, they got a negative pressure. And in other cases, the vents were blocked, or something along the relief vent path was blocked. So they said to me, Colin, what we do now is we turn on our door fan, we see the vent open, and we feel okay about it. So based on that experience, and the experience of many, many others, I thought, well, what we really need to do is to have a pressure vent testing scenario that allows us to not only install a vent when we need it, but to turn on our door fan and see, first of all, will the vent open at all? And if it does open, how much free venting does it actually give us? So the free vent area that the manufacturer specifies might be the free vent area of the vent under ideal conditions if it fully opened, but it needs to also measure the vent path, which is includes all the ducting and the cat flaps or the ring louvers or anything all the way in the path. So that's why we came up with a procedure to actually measure the vents just to make sure that there won't be a problem. Now this is a very interesting little table, and this table occurs in the paper. Just hang on a second. Sorry, I just had some guy start grinding on my door. So what we'll notice in here is that the old NFPA standard versus the new NFPA standard, there's a difference in terms of the hold time evaluation. We get a longer hold time evaluation, and you notice in the case of argon, argonite, Energen, they're all going to be the same. We go from 7.3 to 10.3 minutes, so we get another 3.3 minutes. So around about a 45% increase in the hold time, and at the same time we've got about a 30% decrease in the amount of peak pressure based on the analysis. The reason why that is we have a new test procedure that takes that more accurately predicts hold time and more accurately predicts peak pressure, and that's what I worked on the standard for the last 4 or 5 years, is to get that in there so we could pick out that advantage. You notice that the advantage is not quite as great when it comes to the halocarbons. We're picking up like 10% one way and maybe 20% the other way. But in a lot of cases, this is there could be a lot of cost involved in getting these enclosures a little bit tighter. And in some cases, it might be virtually impossible. So the other thing that we have developed is what we call our 4000 Contra Fan, which is essentially two of our fans. We just, in this case, taped them together, and we've been able to get this up to 10 pounds per square foot at over 4,000 cubic feet per minute, which will enable us to test any vent. So if you have a vent and you're not sure how it's going to open, then you should be testing it yourself, and you can test it with the same blower door fans that you're using in your enclosure analysis that you have anyway. So these are our high power fans. They're in what we call the Contra configuration. One's going clockwise, the other's going counterclockwise, and we have them specially calibrated to measure relief venting. So I'm just going to take a quick look at our poles, and let's see. Okay, so I don't think we asked this one before. So this one is, what kind of enclosure integrity training have you had? We'd like to get a little bit of an idea on that, and I'll just be back in a moment. Okay, so I noticed that a lot of you haven't taken our enclosure integrity training, which I guess now is peak pressure training as well. We are willing to support technicians or anybody really that's taken our enclosure integrity training, but it's very difficult to talk to people that have never taken it before, because 99% of whatever they would ask us would be in our training course, and sometimes they're not even quite sure about the context of the question. So it's important to us in order to offer the kind of services that we can, that we are willing to support all the people that have taken our training and answer whatever questions they want almost without limit. So let's close that one. Okay, so we'll kind of carry on here. So I'm just going to take a quick look at the questions here. A lot of people haven't received the paper. We can make sure that we send you an email and shoot that off to you, no problem. Someone asked a question about how do you determine enclosure strength. I think I answered that one. Now, most of the, someone said about getting a copy of the notes, slides, and so on for later reference. A lot of the material that we have in here is in our training course. They're excerpts from our training course, so they're a little bit out of context. But the key part of the information that we're disclosing here is in the 14-page paper that goes through it. But to go through the rest of the details is probably 100 times the size of that in terms of all the documentation that we have. It takes roughly 24 hours to go through our training course and all the different materials that are in there. So we are willing to provide most of the background information for people so that they understand what's involved. So the next thing we're going to talk about is a very key thing that you will find when you're testing these enclosures is if you can, for example, measure the ratio of the bottom leaks to the top leaks, you can often have a situation where the enclosure can be made tight in the bottom to maintain or to get a good hold time, a little bit leaky or above, which they tend to be naturally. Typical enclosures come in about 25% lower leaks, 75% upper leaks. If we can measure that under NFPA or ISO for that matter, we can put those numbers in and get the advantage in hold time and also in peak pressure. One way to do that is simply to measure the enclosure leakage, then put plastic on the ceiling, as someone is doing here, remeasure it, and the second measurement is the hole in the bottom of the enclosure, which allows the heavier than air agent to flow out. This takes a lot of time, and if you have any leaks in the plastic at all, it doesn't work. So there is a faster way of doing this. I've done plastic on the ceiling 3 times, and I've done this method, which is called the BCLA, below ceiling leakage area test. And all we do is we run 2 fans. We duct 1 fan to the ceiling, and the new gauges that we have what we call a set to 0 function. So we set the pressure across the ceiling to 0, and this fan, the one that's on top, will now measure the below ceiling leakage area directly. And I can do this test in 20 minutes. So I'm saving many, many hours. For a large room, it might take 4 people 4 or 5 hours to put the plastic up. And then if you fail and you have to redo it, you might have to put it up a second time. So it's a bit of a nightmare. All those people that have done it before never want to do it again. Show my screen. Okay, I'm sorry, I was showing the wrong screen here. Hello. I did. Okay, it's updated now. Thanks for letting me know. So let's just back up here. So this is how the flex duct test works in schematic. We have 1 fan, could be above the other one or not, but what's important is this fan at the bottom is measuring the enclosure leakage below the ceiling and measuring this lower leak down here. This fan is simply neutralizing the pressure across the ceiling so it's 0, so that we can isolate the pressure below the ceiling. And for those of you who have never done it before, it seems kind of impossibly complicated, but after you've done a couple, like I say, I can do one in 20 minutes now. And I can do it on my own. I used to have to do it with a helper, but now with the set to 0 function, you can do that on my own. This was one of the first below ceiling leakage area tests. This was a huge test we did of this fairly enormous building, and we managed to save the contractor a small fortune being able to measure the leakage distribution between above and below the suspended ceiling in this very complex setup. So, sometimes it's pretty important. Another version of this is what we call the subfloor only test, where we pressurize the room and pressurize the subfloor and neutralize the pressure across what I call the walked-on floor. So this is a valuable technique as well. This is a picture of a dual-acting vent. I think it's a dual-acting vent, but there is a new series of vents out there that are meant for halocarbons that open in both directions. And it means that you don't have to install 2 vents, you can only install 1. And it should decrease the installation cost dramatically. Most of the vents that do that, or I should say all the vents that do that, are manufactured in Europe, so they tend to be a little on the expensive side, around $300 for a 1 square foot vent, but they do a great job for halocarbons. This is what our new training course looks like. It's all online. Like I say, it's about 8 hours per session. You can go back to it any time and review the material and so forth. It's done primarily in video, so you watch a video section about 15 minutes, ask a series of questions, and then you move on. You can go back and redo the questions as many times as you like. This is what our new software looks like. We'll bring up a version of it later and show you how it works. It's, I guess, kind of up to date. It's expandable, contractible to fit a screen of any size. You can compress any unit as data in an XML file. It's pretty effective. Okay, so that takes care of the presentation part. This would be a good time to take some questions while I hunt up, or maybe we'll do another survey. Since we just talked about PRVs, let's find out what kind of PRVs your company installs. So I'm going to track down our software. There it is. And let's just take a look at. Notice that a third of you aren't installing vents, and maybe it's because your business doesn't install systems, but we felt as a company that there's a huge liability, implied liability, for encouraging people to measure hold times and so on without doing peak pressure evaluation. So we want people to do a peak pressure evaluation. We want everyone to know that we're telling them to do a peak pressure evaluation. If you're going to be doing a door fan test to measure hold time, the peak pressure evaluation is only a few more minutes, and it's all integrated into one package, so it's relatively easy to do. So we'll just give that another minute or two. Now, I wish I could show my other screen at the same time, but I guess I can't. Okay, so let's... Now I notice that there's a very small percentage of you that are installing double-acting vents. Very, very small percentage, so you may not know that they even exist. Now, in some cases, I know that some people in the U.S. are installing a single-acting vent in one direction and a second single-acting vent in the other direction for halocarbons, which pretty much doubles the cost of the hardware, but also doubles the cost, or certainly increases the cost of the installation. Now, someone just asked me, someone asked me a question about calculating the volume of the space we're venting into. What's more important than the volume of the space we're venting into, because that line of thinking assumes that the volume we're venting into is airtight, and it never is to measure the leakage of the volume we're venting into. So typically the volume we're venting into is much larger than the space we're venting from. And in a case like that, you get some credit because of the volume you're venting into, but not much. But I think more importantly is how leaky is the space we're venting into. And if it's leakier than the enclosure that we're venting from, then the pressure across those walls would be relatively minor compared to the pressure across the enclosure walls. So I think that's really the issue, is we may have to, if we're venting into another room, now go and measure the leakage of that room to see how leaky it is. And in most cases, I find that room is so leaky that it doesn't matter, that we're not going to get much pressure buildup in there. So hopefully that answers that question. So let's just stop that little poll, and we'll go back to showing my screen again. Hopefully that's... I'm just going to change something on here to make sure that it actually changes. In there. Okay, doesn't look like it's changing. Let's just try that. There we go. Okay. So, this is the free vent calculator. It follows along in a fairly logical progression. And I'm going to start on a different tab here. I'm going to start from scratch. And I'm going to start on imperial units, and we can change those. I'm going to use the FSSA equations to NFPA 12, or 2012 version. And I'm going to, let's just start with an inert, because they're a little easier To understand, let's go with argonite. Descending interface, initial concentration of, let's say, 35%, a discharge time of 60 seconds, temperature discharge 70, humidity actually doesn't really matter for an inert, doesn't affect anything, enclosure volume, maximum height of the enclosure, minimum protected height, positive pressure limit 250, negative 250, which again doesn't really matter, desired hold time 10 minutes. And so what that tells us here is we need 13,162 square inches of venting. For a 10-minute hold time, we need less than 598 square inches. And if we're going to use the room for venting, we'll say yes, then it says we need a vent of 2,048 square inches. So what can we do about that? Well, one thing we can do is we could use at least some of the room leakage, let's say 500 square inches of it, we can use 500 square inches of it in order to relieve the peak pressure. So that would help a little bit. We could reconsider the fact that perhaps a positive pressure limit of 500 pascals would be more appropriate, and we can see right away that this drops. The other thing that we might take a look at is to look at the leakage split. So in the case of the leakage split, let's say it's 0.2, 0.25. So we now can have, say, 800 square inches of enclosure leakage. So just by looking at the leakage split there, you notice that we don't need a vent anymore. So we've taken an enclosure that needed a vent, we've reconsidered, we've decided that we can do an enclosure integrity test for hold time with a flex duct or plastic on the ceiling in order to measure the leakage split. Now, we don't know what the leakage split is going to be in advance, so what would be required in a situation like that would be to measure the leakage of the enclosure, measure the below ceiling leakage, and start sealing the room until we get down to a point where the room has a below ceiling leakage area that will allow us to get our hold time, and then any excessive leakage above the suspended ceiling on the upper part of the room, at that point really doesn't matter. So it's a way of kind of dialing in the leakage to the extent that we need for hold time, and also leaving enough venting there for your inert agent. So this is a relatively easy process to go through, and I know that system designers are going to say, well, I have no idea what the leakage is, but we know that these rooms are just about always too leaky to begin with. And all we have to do is to control the amount of sealing that we do in the room based on the door fan measurement, which actually reduces our cost of air sealing the room, and all it means is we have to take a measurement, and basically we have a room that's safe from peak pressure, and that will give us plenty of hold time. The other thing that we can do there, if we decide not to go that route, and we'll go back to 0.5 here, the other thing that we can do is we can reconsider the minimum protected height. So in this case, we might decide that we can put this up to 12 feet. And we have the same gap that we had before between, let's see, minimum protected height is 9 feet. So we can now put in, let's say, 1,200 square inches in there for room leakage, and again, we don't need a vent. So by a little judicious playing with the system, we can make adjustments so that we either don't need a vent or we can minimize the size of the vent we want. I'm just going to take a quick look at the questions here, see if there are any of them that are room needs vents. So someone asked, if a room needs a vent, is it necessary to replace more agent? No. The need of a vent just says a room is a little bit tighter than it has to be. We don't actually lose much, if any, agent out of the vents, so that's really not an issue. So someone asked, can we put this information into emails on YouTube? We will have a copy of this webinar on our site, and so that will be available to you. Now, someone asked, under what parameters do we have to inject pressure into the enclosure? I don't understand that question. Okay, we are running the peak pressure hold time calculator now. Okay, so we can carry on. Let's take a look at a more complicated example of let's try a halocarbon and see how that goes. So we're going to change to imperial. We're going to change the agent to, in this case, is FM200. Descending interface, initial concentration, say 9%. Discharge time is 10 seconds. Temperature of discharge, 70 degrees Fahrenheit. Minimum humidity, let's say it's 20%. Maximum humidity, 60%. 60%. We can do the same volume. Maximum protected height, let's just go 9, 7.5, 250 pascals. Okay, so what you notice here, even if we're going to be using the room for venting, and let's say we're going to use 400, we're going to assume we can use 400 square inches for venting, we still require a vent of 174 square inches. Basically need about a one square foot vent for this room. So again, there's a bunch of things that we can do with this. We can change the height of the room. We can change the height of the minimum protected height. We can change the positive pressure limit. The moment we change the positive or negative pressure limit, in this case, if we change that to 500 pascals, all of a sudden our need for a vent disappears. So I think we've actually got this calculator down to a point where it's fairly effective and easy to use. Someone asked a question about does argon need 10 minutes of hold time, 20 minutes? You can put any hold time you like into this calculator. There is no particular need why one agent would need a longer retention time based on the agent. It's, if you read the standard carefully, it's based on the response time. So you can actually have the retention time down to 5 minutes as long as you have a response time that's less than 5 minutes. So what I'd like everyone to do is to, when they get a copy of that, to experiment with it. And I'm just going to bring up our Enclosure Integrity software briefly so that you can get an idea what it looks like. And while we're doing that, I think we've got one more question here, which is what venting equations you use. This is very useful. We want to make sure we've got all those venting equations in our software. So we'll just wait till we get response. We still have most of the people still there. So this presentation is taking a little bit longer than I had anticipated. But I think that we're getting a lot of good information across. I'm just quickly scanning questions here to see if there's anything that people are asking. Okay, so we've got about 57% of you have answered the questions on what venting equations do you use. It looks like a lot of people are using the equations from the manufacturer. You could send us a question or a comment on your little chat box about what equations they are. I know that most of the manufacturers have equations for the inerts that they've been using for quite a long time. So I'd be interested to know what they are. I would like to put all of the equations into our software so you can choose any ones that you want. We'll see in a minute that you can choose a wide range of equations now. Now let's see. So someone asked, how do we determine the positive and negative pressure limits? It's actually based on the wall strength. So you know, essentially, if you say that you've got a wall strength of 500 pascals, that becomes the enclosure pressure limit. Someone said, I don't know what acronyms mean. I'm not sure which acronyms you're referring to. Chances are, if you don't understand them, like FIA or ISO, then you're probably not using it. Zachary is asking, the equations are built into the flow calculation software. Oh, okay. So Zachary's saying that the peak pressure calculations are built into their software. So I guess we take issue with them and don't think they're correct in a lot of cases. Incidentally, it was the clean agent manufacturers themselves that sponsored the peak pressure evaluation project that was done at FICO over a 4 or 5 year period, and it was by far the most comprehensive and open process, and I think as many as 4 or 5 different manufacturers, all the major manufacturers were involved on some level, and most of them attended at least one of our sessions, if not all of them. So it wasn't something that was done in secret, and all this information has become public knowledge. So we're going to close that. That's the last of our polls. Thank you very much for doing that. So right now I'm showing our software, and I'm just going to bring up, there we go. I'm just going to bring up our software. Each of the sections here can be collapsed so that you can take a look at any one section individually. The first thing that you'll notice here under Tools, Options, is that you have a choice of any, I think the Options window has gone and hidden itself somewhere. Let's see where it went. Oh, here we go. It jumped to my next screen. Okay, so I'll just pull it over here. Here we have a choice of various NFPA standards and some of the older standards down here. As we develop new ones, you can access those. There's also a language key down here, and these are all the different languages that we have, so you can change the languages in there as well. For those of you that work internationally, it might be useful. Under Tools, I think Advanced Options, it gives you the choice of, here it is, just showed up. It gives you the choice of changing the venting and peak pressure equations that you want to use. For NFPA, we have FIA and BDS equations. If you're using ISO, we have the same selection. You can use any one of those equations in your analysis, or look at them all if you like. So I think that's pretty useful. So we'll just exit out of that. Nothing interesting about this. This just shows what equipment you're using, building details and so on.